Good morning, everybody. Thank you for coming to this talk about benchmarking. First thing first, if you have any questions, feel free to shout. Do not really wave your hands because those four spot slides are right into my eyes and I don't see a lot of things. And if you have questions, don't wait until the end of the talk. It would not be the most useful thing to do. Ask them right away. So thank you for attending this talk about benchmarking. My name is Pierre Laporte. I'm performance engineer at Datastax, the company behind Apache Cassandra. So who knows Cassandra here? Okay, quite a lot of hands. You guys are awesome. Cassandra is an amazing piece of technology, and that's really really nice to see so many people investing their time and their brain on it. For those who don't know Cassandra, this is a NoSQL database. We usually represent that using rings. I can't see my pointer. Okay, using rings like this, and it has a masterless architecture. So what does it mean? It means mostly two things. First, since we don't have any master, since we don't have any privileged node, it means it can go down. It will not involve downtime at the database level. And this is great, right? It means you can lose a given number of nodes, your application is still up. And also, due to its architecture, it has some linear scalability capabilities. So if you double the number of nodes in your cluster, you immediately double the size of, the amount of data you can store and the amount of requests you can serve. Our goal at Datastax is to make Cassandra the best transactional database, distributed database in the world. And on top of that, we develop our commercial offering where we integrate more Apache Foundation projects such as Solr for faster queries, Hadoop and Spark, Spark is really trendy these days for analytics, and other features, especially for security and monitoring. The monitoring especially for the operation guys. You know, the one who wakes up in the middle of the night are the ones who read Nagios alerts. Just for that, they deserve our respects. So, in the NoSQL space, we see a lot of benchmark, really a lot, and they pretty much all look the same. Now, let me show you how it looks. I'm speaking about throughput, right? So more is better. Usually, it's a man thing. Usually, the benchmark looks like this: our solutions, their solutions, losers, and I didn't even tell you which one, where Cassandra is. Is Cassandra this bar? Is Cassandra that bar? I didn't tell you that. Now, why didn't I tell you that? Well, because it depends on who publishes the benchmark, obviously. So, what is a benchmark? Yeah, what is a benchmark? Well, a benchmark is what you do when you take two pieces of technologies, you put them under the same condition, really, the same conditions, you run the same workloads on those technologies, and then you immediately declare who is the best or which one is the best. Now, if you follow that methodology, you could as well prove that the squid is more intelligent than the cat when it comes down to sorting geometrical figures. So the lesson here is, if you want to have a pet, do not take a cat. Take a squid. A squid can help you sort your socks, do your laundry. It's obviously more intelligent. So that's the lesson here. Now, I've come to realize that whatever you do, you either succeed or learn. And in the performance world, we learn really, really, really often. So what are we here for? Why this talk? Well, we are here to make mistakes. If you recall the keynote from Wednesday, physicists make mistakes all the time. Their theories, most of their theories are proven wrong every day. And this is how they work. We shouldn't be ashamed of our mistakes as long as we do not blame each other. We're not here to blame. Blaming is not part of any scientific method. And plus, benchmarking is also a people exercise. You see a benchmark, you think it's obviously wrong. Now you have to explain that without hurting the person's feeling, right? Because it may be a genuine mistake. maybe no harm was intended. So that's a people exercise. That's a social exercise. We're here to increase our standards, and we're not here to blame. So now let's see how we can fail. Right. We're in the Java conference. I'm a Java developer, so I write a lot of APIs, and especially I have this REST API where I allow my users to log in on my system. It's easy. It's an HTTP request, a POST request on the /login endpoint. Now, I want to benchmark that endpoint. So what I'm going to do is perform 100,000 logins. Now, I'm a bit late on my schedule, and I'm a bit lazy as well, so I could write this huge test data set. But I'm not going to do this. What I'm going to do is, well, I'm going to think and say, nothing is different from one login to another, so one thing leading to the other. I'm going to perform 100,000 logins of one user, because that's obviously the same. Now, I'm going to measure each and every login, starting from the first one, and I'm going to do that during one run. And then I will have my results, right? So, another point is, I'm not the only one late here. My IT team is also a bit late because I asked them to provide me with production-like machines. But yeah, they are late, the order was delayed, and I don't have my machines. So what I'm going to do is run my benchmark on this, which is obviously a pretty good machine. Question? No? Okay. And so I'm going to run that on my laptop. Now, my project manager, he's not into really statistics, performance. He's into Excel spreadsheets and Gantt diagrams. So he asked me for really simple data, right? So what I'm going to do is average all my latencies and give him the result. And as a bonus, I'm going to look at my CPU utilization and do some capacity planning on top of that. Right. I told you we were going to fail. I think that's a good plan. Do you guys see anything, any point in there that is wrong? Okay, shout.
Averaging.
Averaging.
Everything.
More users? Every single point. Yes, yes, absolutely. There is nothing correct in that benchmark. So let's have a look at this. When I say I'm going to do 100,000 login of my system, well, I'm actually not going to answer the right question. I want to benchmark the capacity, the ability of my system to log users in. But if you recall the Cache 101 session from Monday, we have caches everywhere on our infrastructure. We have caches in the CPU, the L1, L2, L3, TLB. We have caches in our operating system. If you use a database, Oracle, Cassandra, it comes with its own caches as well. And if you use a very famous object relational mapper framework, it comes with 3 different caches as well. So the question I'm going to answer is not how many users can I simultaneously log in, it's how cache-friendly my test dataset is. And in that case, it's probably going to sit nicely in the L1 cache. Then I have the clock resolution. Well, this one is a bit, it's not exactly a mistake, it's more of a warning. If my login takes 5 milliseconds, and I measure it with system current time millis, obviously 1 unit of measurement is going to give me 20% variance. So I could use system nanotime, but then I must be really careful, because I will get a number of nanoseconds, but not necessarily an increment on a per nanoseconds basis. It could be incremented every 15 microseconds, and I have to know that. I cannot just think, I will get nanoseconds, I'm good to go. Obviously, there is the warm-up period. So you all know when you start a JVM, the code is interpreted at first. The JVM observes the code, look at how it's behaving, how it's called, and decide which optimizations to apply. Now, it might be wrong at some point. It might have to de-optimize the code as well. If your measurements is during that period, what you are going to have is a lot of noise in your measurement. So you don't want that. You don't really want to measure anything during that period. Now, when I said I'm going to perform one run, what if I had extra background noise, like another developer that was on the machine logging some, or zipping some logs, downloading them to analyze my previous run? What if I had background noise in my measurement? How can I build confidence over my results? Well, with one run, I just can't. So maybe I want to perform a lot of runs and do some statistics over them. Obviously, there was a time, I'm pretty sure it's over now, but there was a time every developer had a Windows XP 32-bit machine with a really big antivirus on it. It's obviously different from a production machine. And finally, there is the average. Well, I'm not going really to talk now about the average. We'll talk about that later. But pretty much the message here is the average, it should not be the only thing you're measuring. But it's interesting. Now, what about capacity planning? Here is a question for you guys. During my benchmark, my CPU utilization was 50%, and I could sustain 1,000 logins per second. So my question to you is, how many logins per second can my system handle?
God knows.
God knows. Anyone else? More than 1,000? Okay, no one is going to suggest 2,000, and that is actually a good thing. The funny part is we are in a conference right now, and there are a lot of traps in this talk. So you obviously know that something is going on. But often our brain, when it sees that, think, well, it must be close to 2,000, isn't it? Actually, no. There are many, many things in our infrastructures that can make us not use our CPU to its full extent. And it's completely wrong to assume that we would have a linear increase. Now, it's very curious because that same brain that we completely unplugged there, it's at its full power when we drive. When you drive, you're in your car, you're computing integrals all the time to deduce where will be where the objects around you will be in 5 seconds, so that you don't bump into them. There is a huge amount of power there. And at some point, I don't know, we completely unplug it. So that was a puzzler using only words and images. Now, let's see what we can measure in our benchmarks. I talked about the average. I personally think the average is an interesting thing to measure, but not the only one. So, when you think about it, the average is the best way to get rid of the outliers. Typically, the average of two numbers, A and B, would be that third number that is equally distant from A than from B. Now, yeah, I think it's an interesting data point, but it's definitely not enough. I think it's interesting because why do we keep hearing about average latencies? Why? I have an answer. Because we demand it. We demand an answer. We talk with our product managers and we ask them, what should be the latency of that particular endpoint? And our product managers, they have a rough idea, and they know one thing. They know that a production environment is not like this. Definitely not. So they know that, but yet they don't want to let us with an unanswered question. So what they tell us is, well, roughly 200 milliseconds. Yeah, 200 milliseconds. That would be good. So let's say on average. And this is why we keep hearing about the average. This is why it's an interesting data point, because this is the vocabulary of our product managers. And we need to speak that language. Now, it's not enough, right? What we may want to measure, or what we should always measure, includes a lot of latency percentiles there. So typically, if I have 1/10 request that is really slower than the rest, what would be an acceptable value. If you went to Conrad's session this morning, he had this nice sentence. If I'm not at the average latency, if I'm at 500 milliseconds response time, does someone die? If not, then maybe that's an acceptable response time for my 90th percentile. And as well, I want to include a lot more percentiles so that I have more precise requirements. Now, how many nines do I add there? You see some dots, some points. How many nines should I measure in my benchmarks? Well, I'm going to go for the cheesy answer. It depends. It depends because if I have 500 users on my application, what does my 99th percentile represent? Well, it's going to represent the 5 unluckiest users of my system. And since it's my system, I get to choose who is the unluckiest users. Who are the unluckiest users? Now, if my system has 1 million users, that same 99th percentile is going to represent 10,000 users. So it's going to be a bit different. And in that case, as my system gains in maturity, I will want to add some nines in my requirements. I will want to target less and less unlucky users. I will want to grab them and get them in the nice spot. And of course, I always want to measure the maximum response time. Not really the standard deviation, by the way. I think it's pointless for latencies. But the maximum response time, we should always measure it. If you're in a video game and the message that is going to be game-changing for one team takes 30 seconds to be delivered, probably because of a network timeout, is it okay to ignore that? Not really. So you always want to measure that. Now, any benchmark starts with a question. And if you went to Kirk and Morris' session on, I think it was on Monday, at some point they started a tuning exercise. And Kirk asked, okay, what is my latency target? What is my performance target? And he didn't got an answer. Now, would you write a recursive function without a stop condition? When you do a benchmark and you don't have precise requirements, that's exactly what you do. At any point in time, you will have a component in your system that is slower than the rest. When do you stop? Well, if you want to stop, you need to have very precise requirements. So typically, that would be a really long sentence, which we're going to see right now. This sentence contains 3 big parts. The first one is the environment. The environment says, how many machines do I have? What is the type of the machine? How many CPUs? How much RAM? What kind of disk spinning or SSDs? What kind of network card? And what is the state of my system when I start my benchmark? Then I have the load, which is what I'm going to write in my load testing framework. What I'm going to do on my machines during that benchmark. And finally, I have my requirements. Now you see here, I have an average latency. And that's pretty okay, because that's what I got from my product manager, but I also got the 90th percentile and the maximum response time. So now I have enough material to work, at least for a couple of iterations. And if a benchmark starts with a session, it ends with an answer that might be satisfactory, that might be not. And that might be not. That's the good part. That's the good part because when you do a benchmark, when you do some performance tuning, the interesting part is not the what, it's the why. Back to this question, okay, I'm not meeting my latency requirements. That's the good news, because now I get to start my profilers and do some really interesting stuff. So having a not satisfactory answer is actually quite good. But anyway, even though benchmarking is fun, please remember that the results are contextual. I told you, environment, load, requirements. Everything defines your context. You also have some compromises if some part of your infrastructure is completely fixed. Your results will be specific to that context, and we should never forget that. So, benchmarking is about statistics. So, let's see some statistical truth. What I like with statistics is that it's the best way to be right and to be proven right by numbers. So, Gil Tene, the CTO of Azul System, has this blog called Latency Tip of the Day, where he has some very nice articles, including this one. It says, when I'm on a website, I'm going to experience the 99th percentile, latency percentile, most of the time, on average. Now, most of you guys should be like, what? And it's really simple. It's a simple, it has a simple explanation. It's based on a study that is from before HTTP2 that says a typical web application had 100 web objects, which roughly means 100 HTTP requests, images, CSS, JavaScript files. Now, what is the probability of me avoiding the 99th latency percentile? It's easy, it's 0.99. But if I issue 100 requests, that probability is 0.99 to the power 100, which roughly means a little bit more than 36%. So, on average, I'm going to get the 99th latency percentile. Now, this is front-end performance, right? So if you want to dig more into this, this topic, there's an open source tool called Yellow Lab Tools, which is really great, which will tell you, oh, in that page, you should merge those files, merge those images, which will help you improve your front-end performance. That's a completely different field than back-end performance and GC tuning and such. Now, back to statistics. We need to talk about normal distribution. My client, these four numbers here, these are what my client kept of a previous benchmarking session. That's all there is. The average, the standard deviation, the maximum, and the median. And my question to you guys is, what is the 99th percentile, roughly? I see some shrug. Any idea? Isn't anyone going to suggest 160? Okay. So that would have been the correct answer, by the way. In a normal distribution, the 99th percentile is roughly the average plus 3 times the standard deviation. So that answer is correct. The problem here is that my client assumed that latency follows a normal distribution and that he could only keep that numbers and still get all the data points back. So that would be a really efficient compression method. But the latencies never follow a normal distribution. And it actually makes sense. Think about it. The normal distribution is like this. What does it mean if my latencies follow that? It means that, on average, my latency is like, well, it's okay-ish. Sometimes it's blazingly fast, but most of the time it's okay-ish, and sometimes it's really, really slow. That doesn't make sense. Actually, if you don't know this quartet named after Hans Combe, the mathematician, this is composed of 4 different data sets that have exactly the same average and standard deviation on both x and y axes. So my client is completely blind. His latencies could be distributed in any of the 3 first graphs, probably not the 4th one. He's completely blind because of that assumption. Latency never follows a normal distribution. Now, who uses metrics here, the metrics library? Okay, a couple of people. Internally, metrics uses a data structure called a reservoir to store the data points. The good point about open source software is that it's not about not paying any money is that you can have a look at the source. And when you look at the source of the reservoir, look at the 4 last words of the Java doc. Every single implementation of the reservoirs in metrics contains those 4 words. So what does this mean? This means that your metrics framework already knows the shape of your distribution. It already knows what the distribution will look like, so when you will send some points, it will not store them. It will keep them based on some sampling and based on that normal distribution. It will pretty much give up the really important metrics, even though you trust it. So you get wrong measurements. Now, how can we check that? How can we fix that? There is a library called HDR histogram, which, if you don't know it, you should really have a look at it. It's well designed. It's used in the high frequency trading world, and it's regarding latency, it's great. You pretty much send all the data points you want. It will keep them. It will truncate them after the 3rd most important digit, which means usually a 0.1% of error. Not a big deal. And what you gain from that, it's that it has a constant memory footprint. So that's pretty cool. You can measure all your data points using the same amount of memory. Plus, you can also graph it in a very, well, interesting way. Look at the part in this graph between the 1st and the 90th percentile. It's completely compressed at the leftmost part of the graph. Why? Well, because we already know what it's going to look like anyway. It's not the interesting part. Our requirements are in the right part of the graph. This is what we are interested in, and this is why we should zoom in the closer we get to the maximum response time. So we've seen a lot of images, but we're in a Java conference, so let's talk about some code. This is a code sample extracted from a very old DGB. Does anyone see a problem with that code?
Integer comparison was equals.
Integer comparison is using equal equal, which means the reference comparison. That's an easy one. So maybe this one was initially using ints, and then it was migrated to use integers. So I'm using reference comparison to compare something that is, well, objects, not values. Now it's a bug, right? Or is it? I have this code sample, which creates an array list of 50,000 integers from 1 to 50,000. And I have my isConsumer method here. And what I'm going to do is iterate from 0 to the number given as a command line argument to check if that reference comparison holds. And when I run my test, I get this. It seems to work for every number between 0 and 127. Why is that?
Integer caches it.
Integer caches it. So in the JVM, we have an integer cache, which caches all the Java-lang integers from -28 to +27. And so when you call integer.valueOf using one of those, one value in that range, you will get the same integer instances. So that was an easy one, right? Now, does anyone know the flag -XX : plus aggressive opts? Kirk, obviously. Okay, what does it do?
Enables super cool aggressive optimizations.
It enables super cool aggressive optimizations.
No idea.
It could be replaced by XX-XX : plus do magic. Yes. Actually, not really. So this flag did enable some really cool optimization in the early days, like Java 5 something. But since then, all those optimizations have been moved to the hotspot trunk and are enabled by default. But it still does something quite interesting. I'm going to fix my code without modifying it. Adding that JVM option to my command line, I fixed my bug. And now I'm good to go. So what's the explanation? What is the possible explanation here? Well, obviously, it must increase the integer cache. And that's exactly what it does. Pretty much that's the only thing that it does. Now the question is, what is the maximum Java-lang integer value? Well, I'm not going to give you that answer because that's part of the fun. Max int? No, that's not this one. No. So if you want to find out, you have three possibilities. You have the runner code. It's on the slide. That's pretty much it. You can look at the print flag final output and compare that with a regular run. Or since Hotspot is open source, you can look at Hotspot source in the argument.cpp file. That's pretty interesting. Now, let's increase our standards. Here is another puzzler. So, we're in 2015. I have a class called dog that has a method first, that calls 1200 times the method second, that calls 1000 times the method third, that creates 1000 objects. Now my question to you guys is, what does it do? But that's going to be a multiple choice question. Does this code yells? Does it not do what we think? Does it measure hotspot? Or does it create roughly 10,000 objects?
Second.
2 and 4.
2 and 4. So let's do this. Who says 1, this code yells? No one. Who says that this code doesn't do what we think? Okay, I would say 20% of the room. Who says this code measures hotspot? 2 people? Okay. And does it create 10,000 objects? 4, 5 people. Okay. The correct answers, I told you, the correct answers, well, they were all of them. They were all of them because we are in 2015. We have a class doc that roughly creates 1.21 gigawatts. So it yells, definitely it yells. Now, moving on to the second part, I'm creating 1.21 gigawatts. The time traveling issue aside, I run that on my 2 gigahertz machine, 2 gigahertz CPU, and it took 169 milliseconds to run. Now, let's think about it. 2 gigahertz means 2 billion CPU cycles per second. If my benchmark run, or if my test run during 200 milliseconds, it means I consumed 400 million CPU cycles to create 1.2 billion objects. That means 3 object creation per CPU cycle. That's not possible. The CPU cycle is the smallest unit of computation that I have. That's not possible. So something must be going on, right? This code actually doesn't do what we think. The code that is executed is not the code that we wrote. Let's see why. Well, let's start with the third method. In the third method, I am creating an object. Now, if I'm hotspot and I'm super smart, I can prove that that object is not used anywhere. The block inside that loop doesn't have any side effect. So it's pretty much dead code. So I'm going to remove it. Now, when I've removed it, I'm left with an empty for loop, which can be eliminated. Now, if I merge the third function into the second one, well, I'm left with an empty loop. And one thing leading to another, I don't have any more code left. So the code that was executed was actually this one. Now, how much time did it take for Hotspot to optimize my code away? Well, roughly 10,000 iterations. That's the default compile threshold of Hotspot. And so in my test here, my test did yell. It didn't do what we thought. It did measure a feature of hotspot called dead code elimination, and it measured that during roughly 10,000 object creations. That's fun, isn't it? Benchmarking is fun. So, let's talk about coordinated omission now. I am a Java developer, so I have this fantastic REST API. I love REST APIs, right? I have this fantastic REST API that has lambdas and method references, and what it does is, well, when I will issue a HTTP GET query on my root endpoint, it will answer hello world. Now, it will also wait 10 milliseconds here, but there is an explanation for that. I think returning a string hello world is probably going to have a latency in the nanoseconds, maybe microseconds range. So I'm going to dominate that with a thread.sleep so that I know in advance what my latency will be pretty much all the time. I know that it will be around 10 milliseconds, maybe 11 milliseconds, not more than that. And you're going to understand why. By the way, does anyone see something wrong with that code? I'm going to take that as a no. So I have this client now. My client is quite simple. It's going to perform 100 queries at a rate of 1 query per second. And it's going to store the latency into an array list. Then I sort the array list, and I print my percentiles. That's simple, right? So do you see any problem with that code? I'm going to take that as a no. So now let's do one thing. Let's run my server, and let's freeze it during 11 seconds precisely. How can I do that? Well, I either have to rely on the GC, which is not an easy thing to do, or I can freeze the server at the operating system level using a 6-stop. And that's what I'm going to do. At the 50th second of my run, I'm going to send a 6-stop to my server, sleep 11 seconds in my bash script, and then send a sigcon to my JVM to unfreeze it. Why am I doing that? Well, because I want to freeze every single parameter in my benchmark. I want to predict exactly what will happen in my benchmark. And now I can do that because I know what my timeline looks like. I have a normal state of operation here and there, and here is the part where bad things happen. That's simple, isn't it? So let's do a pre-run check. I know my throughput. I know my typical response time. I know that my longest, or my server will be freezed during 11 seconds. It will be completely unable to answer any query during that period. And I know that my test is going to last 100 seconds as well. So what I can do is, well, here is the throughput of my benchmark. This is a boring graph. I'm going to perform 1 request per second during 100 seconds. Now, if I do the same for latencies, I'm going to have this. The request that will be sent at the 50th second will have a latency between 10 and 11 seconds. I don't exactly know the precise latency because it depends on when it will be sent, but I know it will be between 10 and 11 seconds. The next request will have to wait between 9 and 10 seconds to get its answer, and so on until the last one. Everyone is okay with that, by the way? Yeah, okay. So, now, the beauty of this benchmark is that I can state my expectation completely. I already know what my 99th, my 98th, my 95th percentile will be. Why? Well, because I only have 100 data points. So you may say that benchmark is really well written. You would be correct. So I know what my outliers will be. I don't know anything about my average, but we already know that averages are pointless. I might have a couple of 100 milliseconds errors in there, but since I'm measuring seconds, it doesn't really matter. And plus, it's not a real benchmark. You know that because you were there in this talk at the 3rd minute of the talk. So you know I've done everything wrong. Don't believe it. Now, I run my benchmark, and in reality, what I get is this output. Let's analyze this. So, the comments aside, I have my 100 data points, I have my maximum response time, which definitely is between 10 and 11 seconds. This is fantastic. I completely agree with that. That's okay. But look at my high percentiles. Look at my 99 and my 95 percentile. What did happen? 16 milliseconds for my 99th percentile. This is definitely not possible. I have my 100 data points, and the reality doesn't match my assumptions. But I told you I froze every single parameter of my benchmark. I did predict everything that had to happen in my benchmark. So I'm in a situation where either I don't have enough knowledge about my system, or there is a bug. And in that case, there is a bug. The system is simple enough so that I can say, yes, it is definitely a bug. The reality is, yeah, I couldn't do a talk in 2015 without a Back to the Future reference. The reality is really different from what I wrote. Once again, I didn't answer the question that I wanted to answer. I did answer another one, and we'll see that. The mistake is in that code. Do you guys have any idea where it is? Yes? I do the request synchronously. Yes, that's exactly the problem. The problem is here. What I'm doing here is I'm sending my request in a synchronous fashion using a thread pool of 1 thread, obviously. I could use a thread pool of 50 thread that would do the same. I would have to send more requests, but I would have the same problem. The synchronous fashion here is the culprit. Now what this means is that when my request will take 11 seconds, it will push the subsequent requests after. It will delay them. It will prevent them from being sent. So my throughput graph actually looks like this. During that part here, I didn't send any query. And yet, since my code was written this way, it was written to send 100 requests, so it added 10 more requests here in that part, way after the 100-second mark. The problem is when it comes down to latency. Look at that. I did completely ignore the bad latencies in that part of the graph, and I replaced those data points with this one. The ones in the part where everything is fine, everything is awesome. This is exactly the problem of coordinated omission. In statistics, we allow for some omission. So if I have a 10 billion data points set, I can remove half of them and still be statistically relevant as long as I remove them randomly. In that case, those data points were not removed randomly. They were omitted in a coordinated way with an event that happened on the server side. I did replace those events because my test has a bug. So what is coordinated omission exactly? Well, it's when I execute my request in a synchronous fashion, and usually my latencies are way under my interval between my threads, but somehow, at some point, I have outliers that are above my interval. And the effect is that it pushes the subsequent request after the bad period. So I told you, still, I had a 99th percentile. So I must have answered the question. What question did I answer? What does my 99th percentile represent? Well, it represents the 99th percentile of the request that went well, not the 99th percentile of all the requests. And that's my mistake. Now, is coordinated omission a frequent problem? Unfortunately, yes. And that's the long version of yes. If you use JMeter, HP LoadRunner, any spec benchmark, or YCSB, you are going to have coordinated omission issues. Now, if you use Gatling, who uses Gatling here? Not a lot of people. So Gatling sends its request in an asynchronous fashion, so it doesn't suffer from coordinated omission. That's actually a good point. So how can we mitigate that problem? Well, we need to test the tester. That's easy, right? You unplug the system in the test, and you replace it with a stub. That is going to do nothing. Now, what could possibly be my latencies if I'm benchmarking a system that doesn't do anything? It must be 0. Average, 90th, 99th percentile, maximum response time. All of them must be equal to 0. If they are not, well, I have a problem in my tester. And also, once you are beyond that point, you can also do the Control-Z 6-stop test, where you freeze every single parameter of your benchmark, you state your assumption before actually running the benchmark, and then you check the results. This is actually an interesting exercise, because you state your assumption, and if you happen to be wrong, well, you have made a mistake, but that's not a problem, because you gain to understand more the system. You get to understand more the system. Now, how can we fix it at the test level? Well, it's actually quite simple. We need to measure the latency, but not starting from the moment the request was sent. We should measure it starting from the moment the request should have been sent. So in that case, my 50th request should have been sent at the 50th second. And if I use that as my starting point, I will immediately see the effect of coordinated omission in my results. I will know that I have a bug in my tester. There is another fix. I can use HDR histogram, provided I know the interval between my samples. And I have two methods here that I can use. So, to summarize, I hope you enjoyed being here. I hope you enjoyed making mistakes. I hope you learned something. Please remember that making mistake is a normal part of operations. It's a normal part of our daily jobs. Recall that every single physicist out there keeps on making mistakes again and again and again. Our theories are proven wrong every day, and this is how they make forward progress. Why should it be different for us? For us. It shouldn't. We shouldn't be ashamed of our mistakes. And also, when you publish a benchmark, don't forget that your results are contextual. If you remove the context out of your benchmark, well, you might as well prove that the United States spending on space and technology directly correlates with the number of suicide by strangulations. And you would be correct because, obviously, that's true. So, keep an open mind, enjoy the fun of benchmarking, and thank you for your attention. I think we have 10 minutes for questions, or 10 minutes of very old music, depending on what you prefer.
Accelerated sandwich deliveries.
Oh, and it can accelerate the sandwich deliveries. Yes, as well. Yes?
Do you see any value in using something like GMH to test a larger system than just a number of data structures?
Do I see any value of using JMH, the Java Micro Benchmark harness, to test bigger systems than just data structures? No, I don't think so. The thing is, JMH has been designed to fool hotspot so that micro-benchmarking becomes interesting and easy to do. And they have succeeded in that. Now, benchmarking a bigger system, well, you would need to understand the threading model behind JMH, and eventually what you will do is I/O operations, which couldn't be dead code eliminated by hotspot, because we don't know what happens, right? So using JMH for bigger benchmarks, I don't think that would be useful. I don't think that would be a good idea. Yes?
You don't want to, with larger benchmarks, you don't want to full hotspot.
And with larger benchmarks, you don't want to full hotspot. Yes, absolutely. Good point.
Right, exactly.
So I didn't touch JMH in that talk because that's a really interesting topic, but I would need 1 more hour. For those who don't know it, it's what they use in the Oracle performance team to improve the internal classes design. We can use that in our applications to check if our algorithm are really well written, but it might be a premature optimization. You might want to pay attention to this. And using JMH means you are interested in algorithmic issues. But what if you actually perform a lot of database queries and it's completely dominating the cost of your application? So you're not even at the algorithmic level. You could spend 2 weeks optimizing a data structure and you would produce something that is interesting, except the results are not visible because you end up always calling the database. Or you end up dominated by the GC itself. For those 2 elements, they are way before the algorithmic issues in terms of cost. Yes? Can you make a comment on Gatling? Yes, of course.
Coordinated omission is a result of back pressure from the server.
The-
Gatling can also suffer from coordinated omission.
So the coordinated omission is a result of back pressure from
One source is back pressure from the server. So when you control
the server to...
yeah, when you control that, the system.
Yeah?
Okay,
Oh,
good way of doing it. Okay.
yeah.
So when you control Z your benchmark, which is a great way of testing for this, then what you're effectively simulating is back pressure from the server. And Gatling is not immune to that effect also. So you can actually get, you can also get the back pressure affecting how Gatling affects it, right? So there's really 2 sources in this case, right? I think for this particular example, what you're looking at is like a fire and forget scenario. If you have a more complicated scenario that you have to simulate, then of course you can have the intermediate interactions be stateful, which means that Gatling has to wait for response. So any of the load test harnesses will do that. So I think in Apache we actually have a coordinated omission plugin being put in so that it can detect it and report on it.
Well, that's pretty sad.
Yeah.
You are really pessimistic. Well, I'm going to end up like this. Any other question? Okay, so I think it's time to turn the music on. Thank you everyone for your attention and enjoy the rest of the conference.